Okay, we're going to look at another modelling paper. Where is the horizon from 2015? Where is the horizon? This table shows the distance to the horizon, y kilometres, at different heights above sea level. So you've got lots of x's and y's. X, it's just told us, is the distance that you are above sea level, and y is the distance to the horizon. So for anybody who doesn't know, the horizon is sort of the imaginary line where the sky meets the earth, or it meets the sea. If you imagine looking out to sea, it's the horizontal line where it looks like the sea ends, but really it just depends on the higher you are, the longer that distance would be, basically. Okay, so we have lots of x's and y's, and we only have 2 points plotted when there's no question on the first page. On the grid, plot the points given in the table. The points 2, 5 and 5, 8 have been plotted. So 2, 5 and 5, 8, we need to plot everything else, so that could take a bit of time. Okay, so 1 and 3.6, just get the scale. It's going 1, 2, 3, 5 spaces to cover 1, so it must be, every space will be 0.2. So 1 and 3.6, 1, 2, 3. 2 and 5 is already plotted. 3 and 6.2 must be here. 4 and 7.1, so 7.1 must be only half a square. You can already see quite a strong positive correlation. So it's looking at the distance to the horizon is growing the further above sea level. 5, 8 is already plotted. 6 and 8.7. Again, it's going to be 0.2, 4, 6, 7 there. Try and get it halfway. 7 and 9.4. 8 and 10.1 must be here, and 10 and 11.3. I've missed 9 and 10.7. 9 and 10, 2, 4, 6, 7. Okay, looks good. Right. So looking at that graph, actually, it looks like it's got a bit of a curve in. So this is a modelling paper. What ends up happening, we're going to use different functions to model a thing. So it will probably start with this simple linear function, then it might go into something else and something else. But you can just looking at that, it does look like it curves around a bit. A useful observation. Right. On the grid, so we've already done the plotting. The simplest way to model the data is with a straight line. On the grid, draw the straight line passing through 2, 5 and 5, 8. So they were the 2 points that were already plotted. So we need to find 2, 5 and 5, 8. 2, 5 is this one, 5, 8 is there, and we need to draw that line and extend it . Okay, so there's the straight line. Doesn't look like it's fitting the data very well, but we'll see what they're going to ask us about it. Find the equation of this line. Right, now it's a straight line, obviously, so your two options are y equals mx plus c, or y minus y1 equals mx minus x1, which you may have seen, you may have forgotten. Looking at this, talking about y equals mx plus c. M is the gradient and c is the y-intercept. We can already see the y-intercept here. We can just read that straight off the graph. It is 3. So I'm just going to write y equals mx plus c. I know that c equals 3 because that's the y-intercept. So then I just need the gradient, right? So think of gradient. Well, it's y step over x step. But really, if you can find an x step of 1, if you look at these scales, it's just 1, 1, 1. It's just every major square is just 1 on both x's. So if we can just, if we just use the 2 points that we knew about, which was the 2, 5 and the 5, 8, I could just draw a little triangle like that. Remember your x step always positive, so to the right, and always do your x step first. So 1, 2, 3, and it is 3 on the axis. So x step is 3. Y step, I need to go up to get back on the line, and it's 1, 2, it's also 3. So the gradient is 3 over 3, it's positive, 3 over 3 is 1. 3 over 3 equals 1. And you could have done that between any 2 points, and with something as simple as that, you could literally just put your pen on the line and say, I go 1 across, I need to go 1 up to get back on the line. 1 across, 1 up, 1 across, 1 up. The gradient is 1. Okay, so if y equals mx plus c, m is 3, m is 1 and c is 3, y equals 1x plus 3, y equals x plus 3. Using this model, what is the distance to the horizon when at sea level? So if you're at sea level, that means that the height above sea level is 0, so you need x to be 0. So y equals 0 plus 3, so that would be 3. We should probably get some units. Go back to here, and by the way, you could have just read that off the graph as well. So when the height above sea level is 0, the distance to the horizon is 3, and it's kilometers. It's 3 kilometers. Okay. Another model for the data is y equals ax squared plus bx plus c. So now this is a quadratic model. Assume that when the height is 0, the distance to the horizon is 0. So we definitely don't use the data we just predicted with the linear model. So we need to assume that when x is 0, y is 0 for this model. So write that down. When x equals 0, y equals 0. Show that c equals 0. So to show that, we need to plug some numbers in and show that it ends up as 0. So we've been told the model is y equals ax squared plus bx plus c. So we've been told that y equals 0 when x equals 0, so we sub into here. So y, which is 0, equals a times x squared, a times 0 squared, plus b times bx, b times 0, plus c. So 0 equals 0 plus 0 plus c. 0 equals c. So c equals 0. Show that c equals 0, that is done. When c equals 0, the model becomes y equals ax squared plus bx, because obviously the plus c doesn't make any difference when c is 0. Use the point 2, 5 to form an equation in a and b. So remember, the 2 is the x and the 5 is the y. So this is telling us that when x equals 2, y equals 5. Okay, so now all we can do, we can just substitute the 5 where we see a y and the 2 where we see an x, but you might consider using a bracket. It's not such a big deal if it's a positive number, but if it was negative, it really would make a difference. But I'm going to write 5 equals a times 2 squared plus b times 2. So like I said, I don't really need these brackets, but you're better off using them, because if you don't use them, then it is going to hurt you when you have negative numbers. So you're better off using them all the time if you're not sure. So this is 5 equals, well, a times 2 squared. 2 squared is 4, so that's 4a plus 2b. Or you could potentially write 4a plus 2b equals 5. The reason why I'm doing that is because I can kind of see where it's leading. It's leading towards simultaneous equations. And the real clue is we've got 2 things we're going to find. We're looking for an unknown a and an unknown b. And if you look at part 2, we've been given another piece of information. We've been given 2 pieces of information, 1, 2, and 2 things to find. It's going to be simultaneous equations. Use the point 5, 8 to form another equation in a and b. So we just do exactly the same thing. but now x is 5 and y is 8. So y equals ax squared plus bx. I just said y is 8. 8 equals a 5 squared plus b 5. So that would be 8 equals, well, 5 squared is 25, 25a plus 5b. And again, I'm going to do the same thing. I'm going to write 25a plus 5b plus 5b equals 8. So we now have our two equations. I'm guessing we're going to have to solve them next, but you never know. Solve the equations in part B and write down your models. So the first one, 4a plus 2b equals 5. And the second equation, 25a plus 5b equals 8. Right, so to do something like this, you would want to make some of the coefficients equal. So you either want to make the a's have the same coefficient or the b's. The a's are quite large, so the lowest common multiple of 25 and 4 is going to be 100. So it's going to make the numbers quite large. So if I was you, I would do whatever makes the numbers the smallest and easiest to deal with, although you do have a calculator. So I would be looking to make the b's both 10. So we do that by multiplying equation 1. I'll call this equation 1 and this equation 2. Multiply equation 1 by 5, and that means every term. And we do equation 2, I need to multiply this by 2. Okay, so this is going to say, once I times it by 5, it's going to say 20a plus 10b equals 25. Equation 2 times 2 would say 50a plus 10b equals 16. Now, what you would do here is subtract, same sign, subtract. So everything's got the same sign, but what I actually mean is the sign of the thing that you're trying to eliminate. So the 10b's both have the same sign, so we need to subtract. And we're going to subtract the bottom equation from the top one. So 28 minus 58, and it does need to be done that way around. Well, or if you did it the other way around, you'd have to consistently do that across. So I am going to do 20a minus 50a, which is minus 30a, and that 10b minus 10b is nothing. 25 minus 16 is 9. Okay, so now we have a is going to be 9 divided by minus 30. A equals, well, 9 divided by minus 30. Is minus 3 over 10, or minus 0.3. Okay, so now to find b, your best bet would be to substitute into whatever looks easiest. So if I go for equation 1, and we're going to say, well, 4a, so 4 times minus 0.3 plus 2b equals 5. 4 times minus 0.3, you can use the calculator at any point, but 4 3s are 12, so 4 times 0.3 is 1.2, and it's going to be minus 1.2, so minus 1.2 plus 2b equals 5. Add the 1.2 to both sides. 2b is going to be 5 plus 1.2 is 6.2, which means that b would be 6.2 divided by 2. b equals 3.1. So now to actually write down the model, remember what the model was. If we go back to number 2, y equals ax squared plus bx. So that means y equals minus 0.3 x squared plus 3.1 x. So there's the model. I probably, if I was doing this in an exam, in fact, even when I did it, I looked at the numbers. When you get strange decimals, you do think, it's a natural reaction to think you've done something wrong. So it's probably not a bad idea just to go to the simultaneous equation solver, which is in equation, and just check. So if I go to simultaneous, I've got two unknowns. Clear anything old, go back again, and I'm just going to put the initial equation in. So it was 4a, so 4 plus 2b, 4, 2 and 5, and then 25, 5, 8. 25, 5 and 8, solve, and that is very reassuring. Just imagine if you did that in an exam. You could even do it before and you know what you're aiming at. So say you know A is correct before you do the substitution, you've saved yourself some work there if you found your error before. So A is minus 0.3 and B is 3.1, so that is great news. Next bit, sketch the graph of y against x for a domain of x between 0 and 10 inclusive. So that means go to your calculator, go to the graph mode. If you've got some old equations in there, get rid of them. And it is minus 0.3 x squared. Remember to use the small minus. Plus 3.1x. Okay, draw. We have not been given a lot of information about y, potentially been told a y min of 0. We have been told an x max of 10. So let's go to the view window. We can certainly get the x's in, 0 for a minimum, 10 for a maximum. Then y min, I'm probably going to start at 0, and if it looks like that's not right, I'll change it. Y max, that probably looks a bit low, so I'm going to go up to 10 and just have a look. I might have to come back, but it's I'm just guessing. I'm guessing the y's. I didn't guess the x's, I was told those. So that's not bad at all, actually. So if we look at that, and it does look like it's here anyway, and actually we were told that when x was 0, y was 0 anyway, so I'm happy with that y min, and it looks like a nice quadratic, which is interesting. Okay, so the model, remember x was 10, we had a y max going up to 10. You do need to put these things in, it's good communication. You could find out where that maximum point is if it makes you feel better. I could do that, and then you sort of know how to scale it. You don't have to do this, but it's at 5.1, so about in the middle here-ish, and it goes up to 8. So if that's 10, well, 8 must be about here, 5 must be about there. And you want to draw a nice quadratic parabola. So up to here, and then down like that, nice and smooth. It should be passing through 0, 0. Just missed it, but not by enough to lose a mark. Right, so there's the model. Now what are we being asked about? Comment on the validity of this model. Right, so it looks like, and it only gives you one thing, so the mark scheme kind of gives you a few things you could write. But the main issue with this model, it looks like you've got a problem after this maximum point of 5.16, which actually I might even put that in because it definitely is relevant for that. So once x goes beyond this point, suddenly the distance to the horizon goes down. And if you look at the original data, well, that really doesn't seem to happen. Remember, this was actual raw data. This was measurements taken. And there's no way that after 5 meters this is going down. It's got this curve bit at the start, so it might be okay up to that maximum point, but it doesn't do this again. So that's a problem. So I reckon it's potentially valid up to 5 meters, but then beyond there it's definitely not valid. So that's what I'm going to write. So valid for the model is valid for, so I'm actually going to put that point in, seeing as we've already calculated it. So that is x at 5.16, 5.17 and 8.01. valid for, and I'm actually going to go up to that point 5.1. So I reckon it's valid as long as it's increasing, and then after that it's definitely not valid. So I reckon just before, you could argue it's valid up to the maximum, but really when it's suggested it has a maximum, it's peaked, it's probably not valid then either. So I reckon it's not valid before that, and then I guess it starts being valid after 0, because actually you think at the horizon, well, we don't actually know about that, but when it was not above sea level at all, or our first model, we don't know, but I would, do we assume it was 0? I don't really know about that at all actually. So I reckon it's probably, we'll say it's valid in there. And if we want to give a reason, I would say because it doesn't fit the data very well at all after this point, because you could say it doesn't fit the data, or you could say because the distance starts decreasing. After this, and it doesn't fit the data. So I've probably written too much then. I think even if you just sort of wrote the first bit, it would probably be okay. If you just put, well, it looks valid for the first half and then it starts going down, something like that would probably get you the mark. They're instructed to try and be positive with their marking. Okay, so we're coming on to another type of model. This y equals ax to the power b. Use 2, 5 and 5, 8 to write down two equations in a and b. Right, so we have been given 2 points on this curve. So y equals ax to the power b. So what we need to do is just substitute the y and the x for the 2 points and just write down these two equations. So the first point, x is 2 and y is 5. So it's going to be 5 equals a times 2 to the power b. 5 equals a times 2 to the power b. The second point, your x is 5 and 8 is y, so it's going to say 8 equals a times 5 to the b. Okay, right. Show that 1.6 equals 2.5 to the b. So what I'm going to do is write both of those equations underneath each other. So they are simultaneous, but they're different. So I'm going to write the bigger one, the one with the bigger number, as in the 8 first. So 8 equals a times 5 to the b. 5 equals a times 2 to the b. So it's saying basically we need to eliminate a. So you might not have seen a lot of this. It's not the only way to do this, but it is the simplest way. Now, things you can do with simultaneous equations like this, you're probably used to subtracting one equation from the other or adding two together. What you can do is divide. I can take equation 1 and equation 2 and I can do 1 divided by 2. It's really, really useful for something like this. So what that means is I do 8 over 5 equals, well, it's a over a times 5 over 2, 5 to the b over 2 to the b. So equals a over a times 5 to the b over 2 to the b. So I've divided everything by everything. So 8 over 5, I think I might leave at that point, or I could potentially turn it into 1.6. 8 over 5, if you weren't sure, you could just use your calculator. But 8 over 5 is the same as 16 over 10. There you go, just to prove it. 8 over 5, 1.6. There's twice, look. Right, so a over a is 1 over 1, which is 1. Now, 5 to the b over 2 to the b is the same as, if you think of your index laws, or just your method of powers, it's the same as 5 over 2 to the power b. Once you're raising both top and bottom of a fraction by the same thing, the same power, then you can do that. So 8 over 5, 1.6 equals 5 over 2 to the power b. I'm just using a power law. 5 over 2 is 2.5, just to prove it. So now we have been asked to show that 1.6 equals 2.5 to the b, so 1.6 does equal 2.5 to the b. So hopefully you'll remember this. If nothing else, remember when you get two nasty looking simultaneous equations, you can divide one by the other. Right, show that b equals 0.5, correct to one decimal place. So the fact that it says show that means you need to use some kind of method. Right, so the way to solve an equation with an unknown in the power is to use logs. So I'm going to write down 1.6 equals 2.5 to the power b, and what you need to do is take logs of both sides. So I'm going to write down log left equals log right. Log 1.6 equals log 2.5 to the power b. Right. This is now your third law of logs, where you can go either way. You can either put a multiplier into the power, or you can take a power out. As a multiplier, we're definitely going to use the second direction. This is why this works. It's all because of the third law, because you can get this out of a power and then we can find it. So this is going to say log 1.6 equals b log 2.5. So that means that b, if you solve for b, we're going to divide both sides by log 2.5. So b is going to be log 1.6 over log 2.5. Go to the calculator. Log 1.6 over log 2.5. And that is 0.513, which is 0.5 to one decimal place. I always think if they're showing that something equals a certain number to a specified degree of accuracy, if you show a bit of rounding, I think that really helps. Find the value of a and write down the whole model. To find a, we can really just as any normal simultaneous equation, we can substitute into either of these two really, or we could go back to that, but there's not really any need. So if I just go into, I'd say what looks easiest is equation 2, but I'm going to use the calculator anyway. So let's just write equation 2, and that says 8 equals a times 5 to the power b. So I think it's good practice to use all the accuracy. It doesn't necessarily mean I'll write the model down like that, because I was asked for one decimal place, but I'm certainly going to use the full number on that calculator. I'm going to use the A and S key. Just before that, I'm going to solve this for a. So if I divide both sides by 5 to the b, so 8 over 5 to the b equals a. So a must equal 8 over 5 to the power, well, b we just said is 0.513. So I'm going to do 8 over 5 to the power of, and I'm going to put a and s, so shift a and s is down there, and that comes up with 3.50. So a equals 3.504. So I reckon you were asked for b to one decimal place, so I think we should probably give a to the same thing, although it doesn't say, equals 3.5 to 1 dp. So the final model is y equals ax to the b, so y equals 3.5 x to the power 0.5. Okay, so that is interesting because it's a square root graph. Compare the model in this question with the data on page 8. Right, so page 8 was where we begun. So seeing as this was quite quick so far, I think we've probably got time to actually look at the data. So if we actually plot the model, it'll probably look quite good. You could even, I mean, you've not got much to write, you could even sort of put it in and have a look at the table and compare numbers. So we can do both actually, it won't take long. So we go menu and graph. Oh, that's not it. Get rid of the previous equation and just type in, so y equals 3.5 x to the power 0.5, which is the square root of x. Okay, we can keep the domain the same, which is fine. And it just looks like I've just lost a bit off the top, so I might just make my view window go up a bit more for y max, sorry. Let's just go a bit higher. So maybe go up to 15. And now it does look, you can really see this curve, it doesn't look bad at all actually. So the next thing we can do is, if instead of graph mode we go menu and table mode, the function will already be in there, but we can do table settings. And what we can do, we can just start at 1, end at 10, and go up in steps of 1, and we can actually compare numbers with numbers. Okay, so now you're comparing 3.5 with 3.6, 4.94 with 5, 6.06 with 6.2, 7 with 7.1. You can see these points are really, really close. 7.82 with 8. So next one would be 8.7 is 8.57. 9.4 is 9.26. At 8 it would be 9.89 from the model, so it's not bad still. 10.5 and 10.7 and 11.067 compared with 11.3. So to me it looks like a very good fit indeed. I would say the model fits the data really well. Very well. Okay, and that's actually it. So really quite a nice paper. I'd say certainly in time wise, but it does have some good things in there. It's got some logs, it's got some straight line graph equations, it's got a bit of substitution, different types of simultaneous equations. So there's really good maths and plotting points as well. But it was quite nice on the time. It was from a few years ago, so maybe it was a little bit more generous, but I think skills wise the level is still up there.